Let us discuss about the crystal bindings. That means the force which holds crystal together. First of all, let us discuss about inert gases. The interaction between the atoms in inert gases consists of van der Waals interaction. Let us consider two different atoms. The positive for each atom, the center of the positive charges and negative charges keep a distance apart. That is x2, and for this atom is x1. Okay. So let us consider the Hamiltonian of the unperturbed system. Let us consider these two atoms are uncoupled, and the Hamiltonian of the unperturbed system is H0 equal to P1 square over 2m plus half Cx1 square plus 1 over 2m P2 square plus half Cx2 square. Okay, and we are considering these two charges. The distance, these two charges oscillates. Okay, center of these two charges oscillates with the frequency of omega naught. Okay, and next let us consider the Coulomb interaction energy of the two oscillators. When we are considering the Coulomb interaction energy of the two oscillators, let us take the Coulomb interaction energy is H1 and that is equal to, this has the charge E, this has the charge positive E, and this has the charge negative E, as well as this has the positive E and this has the charge negative E. So let us consider Coulomb interaction energy. This is in CGS system. I'm skipping 1 by 4, the term 1 by 4 pi epsilon 0. So H1 equal to E square over R. Okay, E into E, Q1, Q2 over R. That is Q1 is E and Q2 is E. So E square over R plus E into this charge is minus E, this charge is negative E, this is positive E, this is negative, this is positive E, and this is negative E. Okay, and when we are considering the Coulomb interaction between these two charges, this is E square over R plus x1 minus x2. The distance between these two charges, this distance between these two charges is R plus x1 minus x2. Okay, when we are considering these two charges minus and plus, these two charges, this plus E and this minus E, we will get the interaction energy as minus E square over R plus x1 minus E square over minus, when we are considering these two charges, minus E square, when we are considering these two charges, minus E square over R minus x2. Okay, R minus x2, and that is equal to E square over R plus E square over, we need to take R outside. R is larger than x1 and x2. R is taking outside, and 1 plus x1 minus x2 over R minus E square over R into 1 plus x1 over R minus E square over R into 1 minus x2 by R. Okay, and this is approximately, this is equal to E square over R plus E square over R into this I am taking as 1 plus x1 minus x2 over R whole raised to minus 1 minus E square over R into 1 plus x1 minus x1 over R whole raised to minus 1, and this is also like this. Okay, and that is equal to E square over R plus E square over R into, I am expanding this term as 1 plus x raised to minus 1. Okay, 1 plus x raised to minus 1 is 1 minus x plus x square minus x cube, etc. And I am skipping higher order terms because the R is in denominator, and if this increases, the order increases, this value becomes small, and I am skipping that higher order terms, and this I will get minus E square over R into 1 minus x1 over R plus x1 over R whole square, etc. And skipping the higher order terms, and I will get like this. Okay, and that is equal to E square over R cube x1 minus 2x1 x2 E square over R cube plus E square x2 over R cube minus E square x1 over R cube minus E square x2 over R cube, and here 1 plus E square x1 square over R cube, and here E square x1 square minus E square x1 square R cube, and this and this will get cancelled, and this and this will get cancelled. The remaining term is H1, the Hamiltonian. The Coulomb interaction energy is H1 is equal to minus 2x1 x2 C square over R cube. So Coulomb interaction energy is H1 is approximately equal to minus 2 E square, this is E, okay, 2e square x1 x2 over r cube. The total Hamiltonian can be diagonalized by the normal mode of transformation. Normal mode means this both oscillators should oscillate in same frequency as well as phase. Okay, so I'm not explaining the mathematical steps which you have learned in classical mechanics. Here I'm just explaining the physical thing. This represents x as symmetric displacement represents this will oscillate, this will compress and expand. This both oscillators will compress and expand together. Okay, and the anti-symmetric displacement xa will represent when this compress, this will expand. Okay, when this compress, this will expand. And the probability is half. This in both modes this can oscillate. So we are taking xs is equal to 1 over under root 2 x1 plus x2, and x anti-symmetry is equal to 1 over under root 2 x1 minus x2. Okay, from this equations we will get xs plus xs plus xa is equal to 1 over under root 2 into x1. When we will add this RHS of this term, we will get 1 over under root 2 x1, and that is equal to under root 2 x1, and x1 is equal to 1 over under root 2 xs plus xa. Similarly, we will get x2 is equal to 1 over under root 2 xs minus xa. Similarly, we are taking this momentum of these two oscillators also like this. P1 is equal to 1 over under root 2 ps plus pa, and P2 is equal to 1 over under root 2 ps minus pa. Okay, so the total Hamiltonian we know, that is H is equal to H0 plus, and H0 is the energy of uncoupled oscillator, and H0 plus H1 is the Coulomb interaction energy. So let us find out H0 in terms of PS and PA as well as XS and X in terms of XS and XA. Okay, so Hamiltonian we know H0 is equal to, for uncoupled oscillator, P1 square over 2m plus half Cx1. C is m omega naught square. C is m omega naught square. Omega naught is the frequency of each oscillators. Okay, the frequency of this both oscillators are same. We have taken as omega naught, and P1 over 2m plus half Cx1 square plus P2 over 2m plus half Cx2 square, and we are substituting the value of P1 and P2 as well as X1 and X2 from this equations, and we will get that is equal to 1 over 2m 1 by under root 2 whole square plus PS plus PA whole square plus etc. Okay, so here our uncoupled Hamiltonian is PS square over 2m plus PA square over 2m plus half Cx square plus half Cxa square, and Coulomb interaction energy H1 is equal to minus 2e square over r cube into x1 into x2. So we need to substitute xs plus xa over under root 2 for x1 and xs minus xa over under root 2 for x2. Okay, and the total Hamiltonian H is equal to H0 plus H1 is equal to PS square over 2m plus PS square over 2m plus this term. When we expand, we can reach in this step PS square over 2m plus half into C minus 2e square over r cube into x square plus PA square over 2m plus half into C plus 2e square over r cube into x square. And we know the general form of Hamiltonian. Hamiltonian H is equal to P square over 2m plus half kx square, where k is the spring constant, and if we compare this equation with this one, we will get k is equal to, here k is equal to C minus 2e square over r cube, and another term is C plus 2e square over r cube. Okay, so so we will get the spring constant k as C plus or minus 2e square over r cube. Okay, and we know the frequency omega is equal to under root k over m, and that is equal to under root C plus or minus 2e square over r cube over m, and that is equal to under root C over m 1 plus or minus 2e square over C r cube whole raised to 1 by 2. Okay, we just have taken the C over m outside, and we will get that is equal to, we are considering this as omega naught. C by m is omega naught. Omega naught into 1 plus or minus. When we expand this one, we will get 1 1 by 2, 2e square over cr cube minus 1 by 8 2e square over cr cube whole square. Okay. So uncoupled energy is U naught. We have taken it as U naught is equal to half h cross omega naught. Half h cross omega naught for one oscillator plus half h cross omega naught for another oscillator, and we will get that is equal to h cross omega naught. Okay. And when we considering the coupled oscillators, these two coupled oscillators, we need to we are getting the interaction energy, the potential energy U naught dash is equal to half h cross omega s plus half h cross omega a. Omega s is symmetric angular frequency and anti-symmetric angular frequency omega a. Okay. So the difference in potential energy delta is equal to delta U is equal to U naught dash minus U naught, and we know U naught dash is half h cross omega s plus half h cross omega a minus h cross omega naught. Omega s is the symmetric angular frequency. From here we will get omega U is equal to omega naught under root c over m is omega naught into 1 plus 2e square over cr cube whole raised to 1 by 2. When I expand this one, I will get half h cross omega naught into 1 plus 1 by 2 2e square over cr cube minus 1 by 8 2e square over cr cube plus etc. Okay, and plus half into h cross omega anti-symmetric is omega is equal to anti-symmetric is under root c over m, that is omega naught into 1 minus 2e square over cr cube whole raised to 1 by 2, and when I expand this I will get this one. Okay, and that is equal to half h cross omega naught plus half h cross omega naught. I will get h cross omega naught, and this terms half 2e square over cr cube and minus half 2e square over cr cube will get cancelled, and this term is 1 by 8 2e square over minus 1 by 8 2e square over cr cube whole square will add up, and that is equal to 2 into 1 by 8 2e square over cr cube whole square minus h cross omega naught. I am ignoring higher order terms of r. Okay, so I will get that is equal to this h cross omega naught. H cross omega naught will get subtracted from this and we will get 0, and the remaining term is equal to minus h cross omega naught 1 by 8 2e square over cr cube whole raised to whole square, and that is this omega naught is the frequency of uncoupled oscillator. H cross is the constant, e square is the constant, is the charge, is also constant, c is also constant, and so we can write delta is equal to minus a over r raised to 6 minus a over r raised to 6. That means the attractive interaction varies as the minus 6th power of the separation between these two oscillators. Okay, this is known as van der Waals-London interaction or dipole-dipole interaction. Okay.